today we will talk about space vector PWM. Space vector PWM is one way of or one technique of switching the converter. So, before we talk about space vector PWM, let us understand what are space vectors. So, space vectors, the origin of space vectors, the origin lies in rotating MMF in machines. Okay. The concept of space vector has come from the rotating MMF in machines. So, we know from our basic understanding of machines that suppose we have 3 sets of windings in, for example, the stator of the an induction motor. If we have 3 sets of windings which are spatially displaced by 120 degrees. For example, let me give you an example here. So, we have 3 sets of winding, for example, like this. These may be termed as A phase, B phase and C phase. These 3 windings are spatially displaced by 120 degrees. If we send a current through these 3 windings which are 120 degree apart in time, okay, in that case, so the current through each of these windings produces its own MMF which is oscillating in nature. However, the resultant of the 3 MMF is something which is a rotating MMF here, okay, the resultant. So, the resulting MMF is having a fixed magnitude and direction. Okay. So, it has a fixed magnitude and it will rotate at the same frequency at which the A, B, C phases are excited. This we know from the basic understanding of electrical machines. The space vector concept also comes from there. What is the advantage of this rotating MMF concept? If you see it conceptually, it is very advantageous to have a single quantity representing the 3 the variations happening in the 3 phases, okay, 3 axes. So, space vector is a concept in which we are kind of like representing 3 variables by a single vector. Okay. So, this is useful in many applications. First and most useful is that you are no longer going to deal with 3 different quantities in 3 different phases. So, you can represent it by a single quantity, and additionally it is very easy to visualize this quantity. For example, we can easily visualize the resultant air gap, resultant flux is rotating in the air gap of the machine. So, this is a single quantity rotating in the machine air gap. So, similarly, space vector is also a very useful way of representing 3 variables, and it is very helpful in visualization of the resultant of the 3 phases working together. But space vector is basically a mathematical concept. Okay. For example, the flux in a machine is really a physical quantity which is residing in the air gap of the machine, but space vector is not necessarily a physical quantity, it is a mathematical concept. So, for example, we can define the space vector of voltage, we can define the space vector of current, but they are not necessarily a physical quantity represented in an actual space. So, these are mathematical concept. So, let us see what how do we define the space vector. So, space vector for example, of load phase voltage is shown here. this is the resultant space vector, or the space vector is defined. So, it is a combination of 3 quantities, and these 3 quantities, since we are talking about load phase voltage space vector. So, VAN is the A phase load voltage, VBN is the B phase load voltage, and VCN is the C phase load voltage. And we are multiplying VBN and VCN by this operator here, and this operator basically helps us to represent the 3 quantities by a single uniform vector, that is VRT. Okay, basically this e to the power j 2 pi by 3 corresponds to the axis, B phase axis, and e to the power j 4 pi by 3 corresponds to the C phase axis. So, basically we are defining the resultant space vector as the instantaneous magnitudes along the 3 phases, phase A, phase B, phase C, multiplied by the rotation of this axis into one single phase. Okay. So, this is what defines space vector. Additionally, we have a multiplying factor of 2 by 3 in the front, and that 2 by 3 is sometimes people use 2 by 3, and sometimes some researchers or some books you will find that they have not used 2 by 3. So, 2 by 3 in this course we are using this 2 by 3 because this is a power invariant transformation. The power from the space vector, when you multiply voltage space vector with the current space vector, then you get a power invariant transformation. So, that is why we are using the 2 by 3. So, in a similar way, like we have defined the space vector of say load phase voltage, we can also define the space vector of current. Okay. The space vector of current is the instantaneous values of the 3 phase currents IAT, IBT and ICT, and then IBT and ICT are multiplied by this e to the power j 2 pi by 3 and e to the power j 4 pi by 3. So, this resultant VRT and IRT have both magnitude and angle. So, they are called space vectors, but the individual quantities this for example, IA, IB, IC, they can be balanced or unbalanced, okay, and they need not to be sinusoidal. So, it can be sinusoidal, but it is not necessary to have these quantities, 3 quantities as sinusoidal. So, we see that space vector is kind of like a mathematical concept, okay, but it is very useful in visualizing, okay, how the resultant of 3 systems is appearing on the plane. Okay. So, in order to understand or in order to visualize it better, we have taken this current space vector here. Okay. So, here on the top we see that there are 3 currents, for example, load currents, and these are we have taken sinusoidally varying currents IA, IB, IC, 3 phase current. Now, the resultant space vector for this 3 phase current is shown by these diagrams here at different time instant. Okay. For example, if we see that at omega t equal to 0, that is at 0 time here, omega t equal to 0, we see that IA vector has the the instantaneous value of IA t is having the maximum value, while IB and IC are negative, but they are equal negative values. So, if we can visualize the 3 axis, which can be written as, So, we can visualize that this is the A phase axis. So, this is the A phase axis, this is the B phase axis, and this is the C phase axis. Okay. So, if we have the currents which at omega t equal to 0 is something like this, that I A is maximum while I B and I C are negative equal values. So, at that point then I A will have the maximum value along this axis, whereas I B and I C are both negative. So, I B has a negative half amplitude on this direction downward, because I B axis is in this direction. So, I B is downward and I C is again negative, but in this direction, because the C axis is like this. Okay. So, we see that the resultant, when you apply the resultant which is found out from this formula here, 2/3 I A t plus I B t e to the power j 2 pi by 3 and I C t e to the power j 4 pi by 3. If we apply the formula, the resultant is this I R here, which is having the same amplitude as I A. Okay. Now, if we take another time instant, say omega t equal to pi by 3, then we see here that I A has reduced to a lower value, while I B has increased and I C has reached the negative maximum. So, the resultant space vector, so I A has reduced in magnitude. So, it is still in this direction, I B is positive and it has become like this, while I C is negative peak. So, which means C axis is in this direction, C is in this direction. So, I C peak is like this here, and therefore, the resultant I R is lying here. So, at omega t equal to pi by 3, the space vector I R initially was here at omega t equal to 0 and has moved by pi by 3 angle to this position. The magnitude of I R remains the same as before. So, in this way, if we go on doing the analysis at other points of time, we will see that the resultant vector is basically rotating in a counterclockwise direction, having or keeping the same amplitude all the time and rotating at the same frequency by which this or dictated by the frequency of the I A, I B, I C signals. And you can understand from here that this concept here is very similar to the rotating MMF concept in the electrical machines. So, we are basically now representing I A, I B, I C, these three quantities by a single space vector, which is I R, having a magnitude at an angle at different points of time. So, this is the major advantage of having this space vector concept. Okay. Now, for a converter which is shown here, we can also have the space vector of pole voltages, space vector of line voltage, we can have space vector of load voltage and etcetera, and load space vector of current, etcetera. So, space vector can be any 3 phase variable. Now, here when we are talking about the space vector, we are basically interested into the load voltage space vector, that is the voltage applied on the load, that is VAN, VBN, VCN. So, this is primarily the space vector in which we are interested in, because this is what we are actually extracting out of the converter and and impressing on the load. So, when we analyze the space vector of the load phase voltages, First, let us understand that what can the converter produce. Okay. Now, the pole voltage of one phase of the converter has basically two switching states, as we have seen here. This any phase SA and this upper and lower switches are complementary. So, this voltage V A with respect to the O point, which is the negative of the DC bus, the VAO voltage can be either VD or 0, right. So, we define two switching states of this phase A of the converter. So, VD is taken as 1 and 0 is taken as 0. So, there are two switching states from each phase of the converter as the two switches, top and bottom switches, are switching. So, therefore, if we, since we have 3 phases, so the converter will be having 2 into 2 into 2, 8 switching states here. Okay. So, these we can also write it as like this, like 0 0 0, 0 0 0 means A phase is having a switching state of 0, B 0, C 0, while if you take 1 0 0, which means A phase VAO is 1 and VBO and VCO are 0 and 0, 1 corresponds to VD voltage. So, this state, for example, this switching state 1 0 0 will be will happen when the upper switch, that is SA in phase A, is turned on, while SB bar here and SC bar here will be turned on. The lower two switches in B and C phases will be turned on, and we can get this 1 0 0 switching state. Okay. Now, we can also understand that, so there will be total 8 switching states. Out of these 8 switching states, the 0 0 0 and 1 1 1, these are called the 0 vectors, okay, or 0 switching states. Okay. We will talk about this 6 active vectors and 2 0 vectors a little bit later when we talk about the space vector diagram. Now, what is the load phase voltage space vector for 1 0 0 combination? So, these are the 8 switching states possible from the converter, and let us find out what is the load phase voltage space vector for any one of this combination. So, when I say 1 0 0, 1 0 0 means A phase is 1, that means VD, that is what is written here, VD, and B and C are both 0. Okay. Now, in one of the previous classes we had derived that VANT is 2/3 VAOT minus 1/3 VBO minus 1/3 VCO. So, if you substitute these values, we see that the VAN is 2/3 VD here, and similarly VBN, if you also substitute these values, VBN is 2/3 VBO minus 1/3 VCO minus 1/3 VO, we see that VBN is minus 1/3 VD and VCN is similarly minus 1/3 VD. Okay. So, these are the instantaneous load phase voltages VAN, VBN and VCN, and their values are 2/3, minus 1/3 and minus 1/3 VD. So, the resultant load phase voltage space vector for 1 0 0 switching state combination will be 2/3 VN plus VBN e to the power j 2 pi by 3 plus VCN e to the power j 4 pi by 3, and if you substitute these values into this equation, then we see that VRT is 2/3 VD e to the power j 0, which means that the resultant load phase space vector for the switching state 1 0 0 is lying with the A phase axis, because it is e to the power j 0 and its magnitude is 2/3 VD. So, similarly for all the other 8 switching state combinations, we can deduce the resultant space vector, and this is shown here in this table. So, for example, V1 is this 1 0 0 and the resultant space vector is 2/3 Vd e to the power 0, and 0 when you have switching state 0, then the resultant space vector is also 0. Similarly, when you have 1 1 1, the resultant space vector is also 0. Okay. For any other combination, you can see 1 1 0, for example, if you can put it into the formula, then the resultant space vector is 2/3 Vd e to the power j pi by 3. Okay. Now, so we can for these 8 switching states, we find that there are 2 combinations 0 0 0 and 1 1 1, they are producing the resultant space vector as 0, and so they are termed as 0 vectors. Okay. The resultant load phase voltage space vector is having 0 magnitude for 0 0 0 and 1 1 1, these 2 switching states. So, this is called as the 0 vector, whereas for other combinations you can have all the 6 active vectors which are termed V1, V2, V3, V4, V5 and V6. Okay. And we can also, so all these active vectors are having the same magnitude of 2/3 Vd, but the angle is changing. Okay. So, we can now plot it, we can now plot it in the plane, in the space vector plane. The space vectors can also be obtained in a graphical way. Okay. And it is quite simple, because suppose you have 1 0 0 combination. So, in 1 0 0 switching state combination, you can have a space vector of 1 of magnitude 1 on the A phase axis and no magnitudes on B and C phase axis. So, therefore, the resultant is 2/3 Vd here. So, when you have a 1 1 0 combination, then you will have 1 here and B phase also 1 here, and the resultant is here 2/3 Vd. Similarly, you can take up the other combinations like 0 1 1 combination. If you have 0 1 1 combination, then you have no vector, means A phase does not contribute any vector, while B phase has 1 and C phase has Vd, and the resultant is 2/3 Vd along this. Okay. So, we see that the instead of all the time going back to the formula, we can also find out the resultant space vector using this simple graphical method. Okay. Where okay. Here A, B, C axis are shown in this. So, the resultant space vector, so we see that there are 6 resultant space vectors with their magnitude 2/3 Vd, and they are at an angle of 0 degree, 60, 120, 240, 300 and 360 degree, and these are the switching states which are producing these resultant vectors. So, there are 6 resultant vectors and 2 0 vectors. Okay. These are the vectors in this space. Okay. These 6 vectors, or the tip of these 6 vectors can be joined with an imaginary hexagon, or in a, this is the boundary. So, you can see the boundary of the space vector diagram is this imaginary hexagon. Okay. And with this imaginary hexagon and the vectors which we have drawn here, we can see that the whole space vector diagram, which is actually a regular hexagon, is divided into 6 sectors, sector 1, 2, 3, 4, 5, 6. So, we see in this space vector diagram, the boundary is a regular hexagon, there are 6 sectors and there are 8 switching states which are indicated in this space vector diagram. Okay, 6 active vectors and 2 zero vectors. Now, so this is the complete space vector diagram, where we can see that the 6 active vectors and the 2 zero vectors are shown along with the boundary of the space vector diagram, and also we see that this space vector diagram is divided into 6 sectors. Okay. These triangular regions are called sectors. So, therefore, there are 6 sectors 1, 2, 3, 4, 5, 6 in this space vector diagram. These sectors are useful when we do the switching on the space vector diagram. Okay. We will see that sometime later. Okay. Now, how to switch? So, now we come to the next topic, which is the space vector PWM. Okay. Now, how to switch these 8 vectors so that the correct voltage is impressed on the load. So, this is the question that we are asking, that okay, we have got a good understanding of the space vector diagram, that it is a there are 8 vectors forming the hexagon, but now the question is how do we switch these vectors. Okay. Basically, we will use one of the very established principle, that is the volt second balance of the principle of volt second balance. That concept we will use here also. Later you will understand that the space vector PWM is nothing but extension of the sine triangle PWM, which we have already studied earlier. This technique of switching the 8 space vectors in such a way that the resultant voltage or current is realized is called the space vector PWM. Okay. So, it is a switching strategy by which we can appropriately switch the vectors for certain time durations. So, the space vectors are switched for certain duration of time in a cycle to produce the resultant vector. Okay. In space vector PWM, the space vector are switched for a particular duration of time in a cycle, and it is dictated by this equation here, which is Vr into Ts is equal to V1 into T1 plus V2 into T2 plus V0 into T0. So, what are these? So, Vr into Ts is the resultant space vector, okay, which is applied for a during the switching timing interval Ts. This total switching interval or switching period is Ts, and the resultant space vector is Vr, which is applied for this time Ts. Now, Ts during the time Ts, in order to realize this resultant vector, or in order to produce this resultant vector, we are switching the 3 nearest vectors which is enclosing this resultant vector. Okay. So, for example, if this is the resultant vector, we see that it is lying in sector 1. If it is lying in sector 1, then this vector and this vector, that is V0 or V7 and V1 and V2, these three are the vectors which are enclosing this resultant vector Vr. Okay. This so as so we will switch these three vectors, this one and this one, for a certain duration of time in a switching cycle Ts. Okay. Now, basically it means that we can visualize it as if like adding some weights to the three corners of this triangle here. Okay. So, if we add weights, the resultant will move depending on how much weightage we add to the three corners of the triangle. For example, what is this weightage? This weightage is nothing but the duty cycle. For example, if we in a switching cycle Ts, in a switching period Ts, if we apply this vector for more duration of time and these two vectors for less duration of time, then the resultant vector will come very close to here. Okay. Resultant vector will come very close to here. On the other hand, if we apply this vector for a long duration of time within the time period Ts, that means this vector is being applied for the largest fraction of the total time period Ts, then the resultant vector will move here closer to this one. It will be far away from these two vectors V1 and V2. So, basically we are as if like we are adding weights to the three corners of the triangle, and these weights are what? These weights are the time for which these vectors are applied. So, for example, T1 by Ts is the vector, is the weight which is T1 by Ts is the vector, is the weight which is being applied on the vector V1. Similarly, T2 by Ts is the weight of V2 and T0 by Ts is the weight for the 0 vectors. So, the resultant Vr will accordingly move depending on how much you add the weight to these three corners. There is additionally we see that the 0 period actually is divided into two 0 periods. Why this is called the 0 period T0? Because we are applying the 0 vector during this time. Okay. So, we are applying the 0 vector for T0 time, we are applying the V1 vector for T1 time and V2 vector for T2 time. Okay. Additionally, this 0 vector T0 is divided into T01 and T07, these two periods. We will see why it is done. This is done to reduce the number of transitions in switching, but we have divided T0 into T01 and T07. Of course, Ts will be the total time period of switching is equal to T1 plus T2 plus T0, which means the sum of the time for which this vector and this vector are switched will be equal to the total time period, total switching time period Ts. Now, one more point to observe is that in this particular case we have taken these three vectors V0 or V7, V1, V2 to realize the vector Vr. Now, it may not be necessary or it may not be it may be possible not to use these three vectors, rather we can also use 4 vectors or we can use V3, V1 and V0. This is also possible. For example, if the reference vector is here Vr, okay, so no, for example, let me take an example. For example, this is the space vector diagram. And there is a resultant vector which is here, okay, the resultant vector which we want to produce by switching V1, V2 and V0. Okay. So, we can take these three as the three nearest vectors which is enclosing the resultant vector Vr. But we may also instead can switch V0, V1 and V3. We can switch them because these three vectors are also enclosing the reference vector Vr. So, one option, so this is the second option. So, the first option was switching V0, V1 and V2, and the second option is switching V0, V1 and V3. Now, which one we will choose, because both these are actually enclosing the reference vector Vr. When we choose the vectors, remember that we must choose the three nearest vectors which is enclosing the reference vector Vr. If we do not choose the three nearest vectors, then the instantaneous error between the vectors and the reference vector will be large. For example, in this case, this is Vr, and what is the instantaneous error? So, this is the V1, V2 and V0. So, this is the instantaneous error. Okay. What is the instantaneous error? See, we are trying to produce the resultant vector Vr, okay. But there is always an instantaneous error between what we want to produce and what we are actually producing from the converter, which means that Vr is the resultant vector which we want to produce, which we wish to produce from the converter. However, we have only V0, V1 and V2 in our hands, because the converter can only produce these 8 vectors. However, I would like to produce Vr which is far away from all these 3 vectors. Okay. So, there will always be an instantaneous error between what we wish to produce and what we are actually producing from the converter, and this instantaneous error is the green arrows which I have shown in this diagram. This instantaneous error is the source of harmonics. You see here the instantaneous error, if I switch V0, V1 and V3 instead of switching V0, V1 and V2, if I switch V0, V1 and V3, the instantaneous error will be more. For example, if you draw it here, the green, the instantaneous error is more when we switch V0, V1 and V3, and so we come to the conclusion that if we switch 3 vectors which are enclosing 3 nearest vectors which is enclosing the Vr vector, then we produce the minimum error, whereas if we choose any other vector, then this instantaneous error will be more than the previous case, and therefore, the harmonic performance or the total magnitude of harmonics will be more if we use those V0, V1 and V3 vectors. So, therefore, we will always try to choose vectors which are the 3 nearest ones to Vr and which is enclosing Vr. Okay. If we choose a vector which is non-enclosing one, for example, if I choose if my resultant vector which I want to produce Vr is here and I switch V0, V1 and V2, what will happen? One of the timing, as per the formula, one of the timing will come out to be negative, indicating that Vr cannot be realized by switching V0, V1 and V2, it will not be possible. So, when we want to realize Vr, we have to choose the Vr which I have shown here, we must choose, for example, these 3 which are the 3 nearest enclosing vectors able to realize Vr. One more thing that we will see later is that if this is the space vector diagram for a 2-level converter. Later we will see some other converters which are called, say, multi-level converters, where this space vectors become more and more dense. Okay. For example, in some other converters we can have, this is the boundary of the space vector diagram of this multi-level converter, but we can have many more space vectors. For example, this is the space vector diagram of a 3-level converter. If you see these two diagrams, the boundaries remain the same in both the cases almost. Okay. The boundaries are same here, but now you have space vectors which are dense, which are closer to each other as compared to the 2 levels. So, this is the 2-level space vector diagram, this is the 3-level space vector diagram, which we will see later how this diagram comes. We see that the space vectors are becoming denser and denser. For example, if you go to 5-level converter, it will even become more and more dense. So, we will have a lot of space vectors, and what will happen there is the instantaneous error. Now, there if you have the instantaneous error, suppose you are switching this Vr, the instantaneous error. So, of course, we will use this one and this one, these are the 3 nearest enclosing vectors. The instantaneous error is smaller. As the instantaneous error is smaller, it indicates that the harmonic performance of the 3-level converter will become superior as compared to the 2-level converter. So, the instantaneous error is what control the harmonics, and we would always like to have the instantaneous error as small as possible. Ideally, the instantaneous error should be 0, because then we produce the Vr as a perfect sine wave. Ideally, it should be then 0, but unfortunately, we do not have so many space vectors available in our hand because of the limitation in the converter. If we had a space vector diagram where these space vectors are infinitely close to each other, then we will get a perfect sine wave out of the converter. Coming back to this discussion about this space vector PWM, we see therefore that Vr into this is the Vr into Ts is V1 into T1 plus V2 into T2 plus V0 into T0, which is again divided into V0 into T01 and V0 into T07. So, the 0 vector both the 0 vectors are used, okay, and they are used half of the time during the 0 period. So, T01 is one 0 vector timing duration, while T07 is the other 0 vector timing duration, and they are usually made equal, that is T0 by 2. Okay. In this example, Vr is the reference vector you want to produce, and you will switch V1, that is the space vector 1 0 0, and you will switch it for T1 duration of time, and then you will switch V2 for the which has a switching combination of 1 1 0 for T2 time, and you will also switch the V0 vector, for example 0 0 0 combination for T0 by 2 time, and V7 vector having a switching combination of 1 1 1 for T0 by 2 time. Okay. So, this is how we will switch these 4 vectors for this time duration in order to realize the Vr vector. Let us see that if suppose Vr dash is in sector 4, this is sector 4. Okay. So, if I want to realize Vr dash, I have to switch V0, V4, V5 and V7, right. So, I can switch say V0, okay, V0 I can switch, that is the 0 0 0 vector, I can switch for T0 by 2 time, okay, and then I can switch V5, which is 0 0 1, and this is switched for say T1 time, and then I will switch V4, which is 0 1 1, which is made by the combination 0 1 1, and it is switched for T2 time, and then again I will switch V7, which will be done by the switching combination 1 1 1, and I will switch for T0 by 2 time. Note that when we do this kind of a switching, then we are always when we go from one switching state to another switching state, there is only one switching transition. Okay. For example, in this case you see that when we go from 0 0 0 to 1 0 0 transition, then only A phase is changing its state, B and C phases are not changing any state. So, B and C phases, the switches will not change their position. In A phase there will be a switching change. Similarly, when we go from 1 0 0 to 1 1 0, or when we go from 1 1 0 to 1 1, sorry, this is 1 1 1. When we go from 1 1 0 to 1 1 1, then also we see that each time we have only one switching transition. This is always maintained in space vector PWM. Okay. Now, so far we have said that we will switch a vector for T1 period, another vector for T2 period, and a 0 vector for the T0 period. But how to calculate this timing duration? How much is T1, how much is T2, etc. In order to do that, we have to get the timing mathematical expression of the timings of this vector. So, here we have taken an example in sector 1. We see that OC is the VR vector or the reference vector which we are trying to switch. Now, in order to get the timing, we can very easily do it by this geometrical analysis. Okay. So, we see that this OC vector is nothing but the vectorial sum of OA and OB. Okay. OC is nothing but OA and OB, and they are forming this triangle. Okay. So, in this triangle we can apply this formula, sides of the triangle, that is OA. So, the angles are, this angle is 2 pi by 3 and this angle is for example theta, that is the reference vector angle. The reference vector is making an angle of theta with the V1 axis, and so therefore, this angle will be pi by 3 minus theta. So, here we can say that OA divided by sin pi by 3 minus theta will be equal to OB. In this triangle we see that in this triangle OA divided by this angle will be equal to AC, which again is equal to OB, AC divided by sin theta, and will be equal to OC divided by sin 2 pi by 3. That is what we have written here, okay, that from the basic geometrical analysis. So, OA by sin pi by 3 minus theta is equal to OB by sin theta is equal to OC by sin 2 pi by 3. Now, what is OA? OA is the, as I told you, if you apply the V1 vector for T1 duration, the net volt second is represented by OA. Similarly, if you apply the vector V2 for a timing duration of T2, then the net volt OB is representing the net volt second, okay, and OC is representing the net Vref into Ts. OC is representing that length Vref into Ts. So, therefore, substituting OA as V1 into T1, OB as V2 into T2 and OC as VR into Ts, we get these two equations, from which it is possible for us to calculate the value of T1 as this expression here. Okay. Here we can say that V1 is having a magnitude of 2/3 Vd. So, V1 is having a magnitude of 2/3 Vd, V2 is also having a magnitude of 2/3 Vd. So, if you substitute here V1, the expression of V1, you substitute here and then you will see that we get up to this expression. Similarly, you can get T2 as this expression here, and T0, that is the remaining of the time for which the 0 vector will be applied. The 0 vector will not cause any addition to the volt second, because it is a 0 vector, its magnitude is 0. So, V0 into T0 will not cause any volt second here. So, therefore, T0 is equal to Ts minus T1 minus T2. Okay. Now, so these are the timing durations for which the vectors V1, V2 and V0 will be applied in order to realize the reference vector VR. So, you can see here, say two cases very interesting is what happens at theta equal to 0. Theta equal to 0 means this green vector is now lying here, right.